Comencem. Okay, so thank you very much for coming to another seminar. Today we have Elisabet Verger. Again, most of you know her. She's a PhD student at the Marine Technology and Operational Oceanography group. And well, she's going to talk about her PhD, I think. So thank you very much, Eli.
Thank you. So hello everyone, I'm Elisabet Verger and I'm a first year PhD student here at IMEDIA, and my supervisors are Ananda Pascual and Baptiste Moret. And today I'm going to talk about From Space to Sea, advancing to understanding of small-scale ocean currents with SWOT satellites and in-situ data. So it's well known that about 70% of the Earth's surface is covered by water. So the ocean is the planet's largest reservoir of atmospheric heat and carbon. So all this heat absorbed by the ocean is redistributed around the planet thanks to these big currents. So the global ocean circulation balances Earth's climate and also makes our planet habitable. So there are three main forces that drive these ocean currents. The first one is the tidal caused by the tide. The second one are the wind patterns, and the third type is the thermaline circulation, which is driven by differences in water density. This last one acts like this big conveyor belt and connect the poles to different parts of the ocean and also the surface and the deeper layers. But today I don't want to talk about these large currents, but rather about the smaller ones, as they are known to be important for this continued uptake of that heat, because this absorption occurs around currents and eddies smaller of 100 kilometers. And they are also responsible for transporting the heat and the carbon from the upper layers to the deeper ones. So they are key to knowing more about, for example, the climate change, of course. But they are also important for other processes, such that they have a high impact on marine ecosystems, distributing and transporting nutrients. They are also responsible for the transportation of pollutants, such as crude oil, debris, and others. And also they are crucial for coastal processes, such as the beach erosion. And knowing more about them can also help us with ship navigation to know more about ocean-atmosphere interaction, among others. So we oceanographers have different ways to study and measure these ocean dynamics. The first way is with in-situ data. We have both ship-based instruments. For example, we have ADCP, which is this instrument that measures the velocity of the column of water. We also have CTD, which is the profiler that do this temperature and conductivity profiles in depth. We have autonomous vehicles, such as the gliders, and also these Lagrangian buoys, which are drifters that follow the currents. The second way we have to study these dynamics is through the modeling, not only to forecast and predict the ocean state, but also to study different processes that we are interested in. And the third way to study the ocean is satellite data. We have also different types, such as sea surface temperature, ocean color, which is related to chlorophyll, and also the altimeters that measure sea surface height. So today I want to talk about this last one, the satellite altimeters, which are key elements to study the current. So they work like by transmitting a pulse of radar to the ocean surface and then measuring the time it takes to bounce it back. So having this time and also know the speed of the light, we can compute this range, which is the distance between the satellite and the sea surface, and also knowing the satellite altitude, because we know the orbit, we can compute the sea surface height, which is this. Here I want to clarify that we usually use two different terms to refer to that. The sea surface height takes as reference the ellipsoid, while the absolute dynamic topography is the same, but it takes the reference the geoid. So we use both. So you may wonder how we use all these sea surface height measurements to study or to better understand the ocean current. So you have to keep in mind that in the open ocean, the movement of water is caused mainly by two main forces, which are the first one is the pressure gradient force, due to this difference in sea surface height, and it tends to pull the water from high level to lower level. And then we have the Coriolis effect, which is due to the Earth rotation, and that pulls the water to the right in the northern hemisphere, into to the left in the southern hemisphere. So when we are in the open ocean and a large scale, we can assume there is a balance between these two forces, as we can see here. Well, the F is the parameter of Coriolis that depends on the latitude. G is the acceleration of the gravity, and this derivative is the slope between these, the different heights. So when we assume that we have this balance, we call it the geostrophic balance. And here we can easily isolate the velocity of the current. So with this assumption, the larger the slope between different heights, the stronger would be the current. Also, when a strong current encounters an obstacle, such as the coastline or other water masses, the flow becomes unstable and it starts rotating, creating what we call the ocean eddies. So there are two main types of ocean eddies. The first one are the cyclonic eddies, which rotates counterclockwise, and it's characterized by this low here, this depression in the sea surface angle, and also by this upwelling of colder, deeper, and usually richer in nutrient water. And the anticyclonic is the opposite. It has a clockwise rotation, and it's characterized by this downwelling and also by this this high in the sea surface, and also this bowl shape of the isopigma. Here, I just wanted to mention that this assumption, the geostrophic assumption, explains a lot about ocean dynamics, but not all the currents are geostrophic, because this approximation assumes that the flow changes slowly and also that the velocity gradients are small. So at smaller scales, the ageostrophy become more important. But however, we use the altimeters because they can be used to measure the geostrophic component, and which explains most of the dynamics of the open ocean. So as I was saying, the conventional altimeters have greatly advanced our knowledge about the large currents during many years. But however, they have a spatial resolution limited. For example, in the case of the Mediterranean Sea, they don't allow us to see structures smaller than 130 kilometers. And that's why today I want to talk about SWOT, this new satellite altimeter. Diego already talked about it 2 weeks ago in the seminar. He focused more on coastal areas, and I'm going to focus more on the open ocean. So the Surface Water and Ocean Topography, the SWOT satellite mission, was launched in December of 2022 by the NASA and the French Space Agency. And it is a major breakthrough in the observation of the ocean from space, as it measures with a spatial resolution 1 order of magnitude higher than the present altimeters, meaning that now we will be able to see structures of sizes between 15 and 30 kilometers. And also the difference is that while the conventional altimeters measure point by point, SWOT offers us like this two-dimensional vision. So after its launch, SWOT started with a SWOT validation and calibration phase, of 90 days, where when it provided daily observations of sea surface height in specific areas of the world. So we were lucky because one of the selected areas was the Balearic Sea. And yeah, also during this validation phase of SWOT, SWOT inspired the International Adopt the Crossover program. And within this initiative, we had more than 30 in-situ experiments around the world aimed to validate SWOT data and to know, and to assess its performance. So the PATSWOT project from SOCIP and IMEDEA was funded by the Ministerio de Ciencia y Innovación, was the Spanish contribution to the SWOT Adult Crossover program. And it has two main goals. The first one was to participate to the SWOT validation activities collecting in-situ observations, and also to characterize small-scale dynamics, combining these in-situ observations with satellite data, and also with model simulations and machine learning techniques. Yeah, so in this framework, we did 2 oceanographic campaigns in April and May of 2023 in the Balearic Sea to assess SWOT's performance in this area. So we didn't decide the area of sampling until a few days before the first planned experiment, because we wanted a structure small enough to compare with SWOT and to see, to compare it with our in-situ data and to see how it was performing. So a few days before the first planned experiment, we detected this small-scale anticyclonic eddy of 20.5 kilometers of radius in SST images. And then we decided to go there because it was also just inside one of the passes of SWOT, so it was a perfect target. Yeah, here when I'm going to talk about the conventional altimetry, I'm using this DUAX, which is a product that made several satellite missions. And SWOT, I'm using the L3 version 1 product. So here it was impressive how SWOT captured this eddy also with much higher detail and magnitude than, for example, in the case of the DUAX. Yeah, here we can see the sampling strategy we followed in the both experiment altogether. The first one took place between 25th and 29th of April of 2023, and the second one from 7th to 9th of May. And in total, during both, we obtained all that measurements from two gliders, these red lines. Also continuous measurements of a moving vessel profiler, which is a profiler that measures conductivity and temperature along the ship trajectory down to 200 meters depth. Then we also have the ADCP that measures continuously the velocity of the water column, the thermosalinograph that measures salinity and temperature in the surface. And we also deployed a total of 45 drifters, these buoys, which are these pink points. And also we performed different CTD stations at different depths. So starting to analyzing a bit more into results. Yeah, before the experiment, we already had drifter in that area that was trapped by the eddy, and also here I show 6 SVP drifters, this one that was already there, and 5 that we deployed during leg 1, and it's clearly see this how they were trapped in this anticyclonic eddy. And also what is more impressive here is here I show a map of SWOT sea surface height and how the contours of SWOT matches with the drifter trajectory. Yeah, and here the DUAX map we have, which has low resolution and also is not that accurate in measuring its center. Here I want to show you a bit more the structure of this eddy in depth. Here we have this glider section, which took 3 days to cross the eddy, and the transects down to a depth of 700 meters. What's important here is that we see this cold and fresher core of this eddy, and the shape of the isopycnol that I was mentioning before when talking about anticyclonic eddies, right? At about 400 meters and so on. But in the surface, we don't have the same shape, and this is because this eddy was like trapped in the below the thermocline, and that's why we call it an interthermocline eddy. So now I want to see if, as I also said before, this anticyclonic eddy gives us this shape, this height in the sea surface height. So to compare the in-situ data with the data that the altimeter gives to us, the sea surface height, we can use this formula, which is the dynamic height, and which is related to the density in all the water column. So using this, that's why here I show this density section is the same that what I was showing before. And then thanks to this potential density anomaly transit, I can compute the dynamic height that we can see here in blue to compare to the data that SWOT and the DWATS gives to us. So we interpolate spatiotemporally the satellite data in the same transit, and then we compare it. And here it's impressive how SWOT is in good agreement with the glider, and also how we capture these gradients and this higher magnitude of the eddy that we are also seeing with the glider. And here the DWATS it's plain now. So we can say that comparing SWOT sea surface height and glider dynamic height, we see a significant improvement over conventional altimetry. So here the final comparison I did was with the velocities of the cross-section velocities obtained with this ABCP. So here we have this transit crossing the eddy, and the first thing that we see is this change in the direction of the arrows, which indicates us that it is clearly an anticyclonic eddy. And here in this same transit, but onto a depth of 200 meters, we can see again this change in the sign of the velocities. So then to compare that with the velocity that SWOT and DWATS gives to us, we can again interpolate in the same transit and do these comparisons. And here again we can see how SWOT in orange and the ADCP in blue and in a level of 100 meters are in very, very good agreement in comparison with WACS. So here I put all these results in a statistic way. So the left y-axis is the RMCD between the instrument that we are comparing, the glider ADCP velocities and drifters velocities, versus the DWACS in this darker blue and the SWOT in this sky blue. And the right y-axis is the percentage of improvement of SWOT with respect to DWACS. So in all the instruments, we can see an improvement of SWOT. In the glider dynamic height estimation, it's more than 30% of improvement. In the ADCP velocity cross-section velocities, it's 60% of improvement of SWOT compared to DWACS. And in the drifters velocities, the two components, the meridional and zonal, we have also an improvement between 20 and 30%. So to conclude, I want to highlight that one of the major international challenges in oceanography for the next decade is to understand the three-dimensional dynamics associated with this small scale currents. So thanks to SWOT, now we are entering a new era for understanding all these dynamics, and also that multi-platform observations are key to complement these observations and also to going down to finer oceanic scale. And that all this is thanks to an international effort and collaboration between different groups. Here I wanted to show this beautiful image, which is the 21-day orbit of SWOT, which is the orbit we have right now, and that covers worldwide, and you can see these finer currents in the map. And yeah, also the specific conclusions about my work is that we collected these in-situ measurements of this small-scale introthermal eddy in the Balearic Sea during the SWOT sampling phase. And we can say that SWOT properly represent the sea level signature of the eddy and also the geostrophic velocities. And we see a significant improvement compared to conventional altimetry. My future work is going to be to reconstruct and integrate all this data together to have like this three-dimensional vision, and also to assimilate SWOT data into a high-resolution model. This is the BIMO model. And yeah, during this past SWOT project, we have done many outreach activities. The first one is this documentary that you can watch on YouTube about the campaigns and the importance of ocean currents. We also had this collaboration with schools where they adopted one of the drifters that we deployed during the campaigns. And yeah, also today, Diego and I will be in the Kasha Forum for the Urban Research Night talking about SWOT, and Baptiste is going to be in the Par de la Mar presenting the documentary. So we hope to see you there. And thank you.
Thank you very much, Eli. Any questions?
I have a question.
Yeah.
Oh, I understand that the resolution of this altimeter provides actually a higher or more precise view of processes that are the dynamic processes that are occurring in the sea. So, to which point the agreement between the actual physics or physics measured by the instrumentation and the altimeter are biased, because from the reference geodesic or geodic geoid that the altimeter is using, because I understand that the altimetry uses a reference geoid.
The
A reference.
yeah, reference level, yes.
So even though you improve very much your altimeter measurements, you also have errors or biases that are related to that reference surface. And I don't know how much of the disagreement between measurements and real currents are due to that reference surface. I don't know if you have an estimation of that.
I don't have an exact estimation, but I know that nowadays the reference level is quite accurate, and the difference that we are seeing probably due to this geostrophic component that I was mentioning. For example, when you have strong winds, that the geostrophic assumption can explain. So I think the difference between the altimetry measurement and in-situ data. Yeah, of course, it can be maybe influenced a bit because of the geoid estimation, but I think the differences are mainly due to this geostrophic component. But I'm not sure if I'm right.
But there are continuous improvements on the what we call the mean and methodology, that is the program with UI. So students, it is something that in parallel you have to improve this and make the approach. We have contributed to the labor and see I remember there was a big eddy that was artificial due to the wrong estimation of the GeoI. And when you go to smaller scales, and also the corrections, like because you have to apply many corrections, and one is to remove the effect of wind and pressure before you combine all the data, and we are seeing that the fields that we have are too low resolution for this, so that can be another source of problem. But still, it's pretty good.
I have a question, how your results of fast SWOT will be implemented into the data workflows of the satellite. So let's say if you, I mean, there was a good agreement of the data, but maybe it can be still improved. So I would wonder if you now pass this to NASA, will they correct the satellite in a whole, or will it just for measuring the Mediterranean, will it be apply a certain
I think
adaptation, or will it just not adapt SWOT at all, but just change the post-processing of data?
it's more that they are releasing different versions of data continuously because thanks to all these validation campaigns, they know more about which kind of problems that can have the satellites. And for example, we saw this displacement in the eddy between days. It wasn't like exactly in the same position. So now, yes, we have sent that to them, and they are seeing, I mean, how they can correct it, but applying different corrections. They are continuously improving, for example, the tidal correction or the correction due to waves. So, they are like, I think, implementing these suggestions more in the post-processing, but not in the measuring. I don't know if that was your
Yes,
question. Okay.
Any other question? Well, so we can leave it here. Thank you very much.